So what is Wellbore phase redistribution? While you have single phase flow in the reservoir, you probably have multi-phase flow in the wellbore. And that is probably because your wellhead pressure is lower than your saturation pressure. So when you perform a shut-in, the heavier fluid is going to fall down in the well and accumulate at the bottom of the well. And that will change the density below the gauge over time. So the pressure that you've got at the gauge won't be a direct measurement of the pressure of the perforation. It is important to know that all types of producers may experiment wellbore phase redistribution at shut-in, even a dry gas well due to condensed water. And without a downhole gauge, the problem will be more severe. So here I'm going to show you a quick example from a gas condensate well, and we're going to see the typical response on the data plot. So let's assume the well is flowing and pressure decrease this way. We've got a drawdown, and then we perform a shut-in. So pressure increase this way. The pressure at the gauge is equal to the pressure of the perforation minus the hydrostatic term, which is rho for the density times g, the gravitational constant, times h, the vertical TVD height between the gauge and the perforation. So when we perform the shut-in, what might happen is the liquid droplets might fall down the wellbore. It might accumulate at the bottom of the well and in some occasions form a liquid-gas interface. As more and more liquid droplets fall down the well, this gas-liquid interface might move up. And if this is the case, then the fluid below the gauge is getting heavier and heavier. Density is getting larger and larger, and what we may tend to see on the pressure at the gauge is a stabilization, or even on some occasions a decrease in pressure, like I've shown you here in this example. If the gas-liquid interface stabilizes below the gauge, or even past the gauge, then the density below the gauge is going to be constant. Okay, so this term is going to be constant, and now the pressure of the gauge will be again a direct measurement of the pressure of the perforation. So we will end up with a true PBU response. But on some occasions, liquid might be reinjected in the reservoir due to, let's say, gravity or gas expansion in the tubing, and then the liquid-gas interface might go down the well like this. And now again, the density below the gauge is changing over time. The fluid below the gauge is getting lighter and lighter, this term smaller and smaller, the density. So now the pressure of the gauge will increase, not only due to the PBU, but due to this density getting smaller and smaller, or the fluid getting lighter and lighter below the gauge. It will have the same effect as a PBU, and it will be quite difficult to see. The problem as well with reinjection of liquid in the reservoir is that it can take quite a while. So for example, a couple of days. Okay, so I've shown you with a quick example a very characteristic sign of wellbore phase redistribution with a pressure that decreases this way. But you don't need to see this to have wellbore phase redistribution. Actually, you might end up with what you think is a perfect PBU data, but this data will be affected by wellbore phase redistribution. And that is the case, for example, if the fluid is getting lighter and lighter below the gauge, as the liquid is getting reinjected, you might not see this problem here. So what are the sort of impact on the derivative? Well, if we've got a decrease in pressure, as we saw on the previous example, then you will have a break on the derivative. As pressure decreases, the derivative is going to be negative, and you will see this discontinuity as on the red response here. But you could have different type of response, and the very famous sign of Wellbore phase redistribution on the derivative is this V shape here. Okay. Sometimes you could have a response as the one in pink with another straight line which has been shifted towards the right as the compressibility of the system increased due to gas. You could have the response in black and in green here. So Wellbore phase redistribution is going to mask any flow regimes that you have in between. Some derivative features can be mistakenly taken as flow regimes. For example, for the black response here, we could assume that we've got a zone near the wellbore at a lower permeability. So that could be due to different reasons. We could have a multi-phase region now in the reservoir with a lower effective permeability. We could have a limited perforation. Or for example, we could assume this is the permeability around the wellbore, and further away from the well, we've got an increase in KH. Same for the pink. If you've got the fracture behavior, you could assume that this is the fracture behavior, and you've got your radial flow regime across the frac height, and this decrease in the derivative could be interpreted as a limited frac height, so spherical flow towards the frac. In the worst case scenario, the shut-in period is useless. For example, here, if we've got a PBU less than 100 hours, then we won't be able to use the data. Or we could use it, but we will make some errors. There are two interesting SPE papers on this, which I recommend you to read, and more examples will be available in the library as well. Sometimes we may see phase redistribution on water injectors, and especially if you've got a water injection well in an hydrocarbon region with some small volume of injected water, hydrocarbon may re-enter the well. And during shut-in with this PFO, for example, you might see a pressure that stabilizes or even go up as hydrocarbon and gas enters the well. That will be translated by a drop in the derivative, like in this example. And this information could be used to start or stop injection of glycol in the well to try to avoid hydrate formation. We can see other features similar to phase redistribution on water injector, and especially the V shape on the derivative plot. And these are mainly due to temperature effects. So what happened during shut-in is pressure decrease, and your temperature is going to increase, and that might affect your density. And you might tend to see a stabilization on your PFO, and even in some case an increase in the pressure, like in this example. Okay, so what can we do to detect phase redistribution? Well, if we've got different gauges in the tubing, you can compare this gauge to detect density changes and fluid movement. That might be the case for exploration and appraisal well. You could do a derivative overlay, but it is important to know that a consistent derivative response is not a guarantee. So if you've got a consistent response on your derivative plot with different PBU, that doesn't mean that you don't have phase redistribution. Some solutions to minimize the problem. Well, we should try to place the downhole gauge as close as possible to the perforation. And in the production context, that means lower than 150 feet from the perforation. For exploration appraisal, we should try to go as low as 50 feet or lower from the perforation. We could apply a downhole shut-in that could help to minimize the phase redistribution. We could do some experiment on the flow rate just before shut-in, so we could try to flow the well at highest rate as possible to try to lift the heavier fluid in the wellbore. Or we could even try to play with the flow rate to try to change the flow regimes. Certain flow regimes are more likely to create phase redistribution. Or we could use other sources of information, so some drawdown periods, permeability from the core, etc. Okay, well test support. Well, you can go to testwells.com. You will have more and more training course with the basics in well test analysis, basics in surveillance, and as well in the well test group you will have access to some newsletter, some new presentations, and audio conference. Alright, thanks very much for your attention.